Welcome, everyone. This is the first year that Robo program is offering a capstone project, and we have our first group that are um, going through this capstone process. So welcome, everyone. So we've got three students, Zachary, Amar, Mohanty, Keyan, Zhai, who will be talking about an automated at-home fall assessment for elderly using computer vision. So let me I have to let you share screen. Okay, whenever you're ready.
Great. Can you guys hear my screen? See my screen?
Yep, looks
Great.
good.
Awesome. So, hi, my name is Amar Mohanty. I'm with Keyan, Zhai, and Zach Block. And today I'm going to tell you guys a story about how our semester-long Capstone project started as a camera-based fitness app for the elderly and then transitioned into an automated at-home fall assessment tool. This whole project of ours started due to my personal experiences with my mother. Before COVID, my mom lived a very fulfilling life where she regularly attended group fitness classes with her friends. Ultimately, this all changed after COVID because due to her age and prior health conditions, she was unable to safely attend fitness classes. And this dramatically affected her quality of life because that fitness class was not only her main fitness activity, but also her main social activity. And as I dived deeper into the problem, I realized she wasn't alone. There was a systemic problem among older adults, whether it was a lack of access, fears of injury, low motivation, or at risk of COVID, they all suffered major barriers to regular exercise. As a result, I wanted to create a startup to fix this problem. So I recruited Keyan and Zach, and we coupled this startup with our Capstone project so that we could use university resources and work with Dr. Mark Keyan. Our initial motivation for this project was to address the major barriers for regular exercise for the elderly by creating a camera-based fitness game. We were cognizant of the fact that three tech bros in their mid-20s don't know much about the day-to-day experiences of all older adults, so we developed technology in parallel with robust customer discovery. To develop a camera-based fitness app for the elderly, we had to do real-time pose estimation. Because we wanted to develop a practical solution for the elderly, we had to do pose estimation using a computer with no GPU and a webcam. And we found that these hardware constraints severely limited our ability to utilize many off-the-shelf pose estimation packages available because they often required powerful GPUs and CPUs for real-time performance. We attempted to improve the frame rate of those pose estimations using optical flow, but it suffered from poor accuracy. After more research on pose estimation on low-powered computers, but we found a package known as Mediapipe, which offered good real-time performance on low-powered computers. However, its accuracy wasn't as great. We also researched how to benchmark the pose estimation and worked on connecting the pose estimation algorithms to the Unity game engine, which is shown right here at the bottom right corner. While all this was happening, we also participated in the NSF Regional I-Core program, which focused on customer discovery research. Through this program, we were trained on how to conduct effective interviews, and we were tasked with conducting 20 interviews with experts and customers. We interviewed seniors, physical therapists, chief medical officers, and health administrators. Through our interviews, we found that we had correctly identified that adherence to regular exercise was difficult with older adults. But for our product to be successful, we had to integrate into that person's lifestyle. And as we thought about our solution more, we had two glaring issues with our product. The setup for positioning a camera so your body's properly framed was too difficult, and explaining how an avatar represents you in a game was too foreign of a concept for older adults. And by that time, we were 2 months into our development, and we recognized that we needed to do a pivot. And one of the most common comments that we heard from experts was regarding elderly falls, because 1 in 4 65-year-olds and older fell every year, and over 3 million are treated in emergency departments. We noticed that also most of the market solutions focused on fall detection, but that was too late. We wanted to identify a fall before it happened, and it turns out the CDC did too. They had developed the STEADY algorithm, which is a fall assessment tool used by physicians. It's a fairly basic exam. And we realized we could automate the process so that it could be done at home by any person. In particular, we focused on their evaluation of gait and strength, which involved 3 tests: the tug test, the chair test, and the 4-step balance. We envisioned the test being conducted at home in a 12-foot by 12-foot space with a computer and webcam placed on one side. Our test would be done with one helper and then the elderly person. The helper would set up the system, start every test, and ensure that the elderly person doesn't fall. Our tool will guide you through each exam and evaluate if you pass the test. As shown on the slide here is our workflow of our algorithm. We will ask the user to input information about themselves, and they would get a preview window describing the test and ensure that they're in the frame. After the user performs each of the 3 tests, we'll automatically generate a report detailing if they're at risk of falling. Here's an example of the output of our sample report. Now I'm going to hand it off to Keyan, who's going to go in depth about each test and exactly how the algorithm works.
The first test is the timed up and go test. The goal of this test is to assess the mobility of the user. To do so, we measure the time it takes the user to stand up, walk 10 feet, and sit back down. If the user takes more than 12 seconds to finish the tug test, then they're at the risk of falling. As you can see in the video, our algorithm automatically measures the time it takes the user to stand up, walk, and sit back down. To automate the tug test, we utilize the output of Mediapipe to get the X and Y pixel coordinates of the left and right shoulder. We leverage the fact that the user is initially seated to determine if the user is sitting, standing, or walking. We know that when the user stands, both shoulders will go up in the Y direction. As a result, we measure the distance between the current frame shoulder Y coordinate to the initial frame shoulder Y coordinate to determine if the user is standing or sitting. We also know that when the user walks back and forth, their shoulders will translate along the X direction. Consequently, we measure the distance traveled from the initial position to the current position to determine if the user has walked far enough. When the user is seated and traveled enough distance along the X-axis, we stop the timer. The second test is the 30-second chair stand test. The goal of this test is to assess the user's leg strength and endurance. To do so, we measure the number of times the patient can stand up and sit down in 30 seconds. Based on their age, gender, and the number of chair stands, we can assess if they're at risk of falls. As you can see in the video, we're able to accurately count the number of times the user does the chair stand. The timer will automatically stop after 30 seconds and will evaluate if the user passed or failed the test. Once again, we use Mediapipe to do the pose estimation of the left and right shoulder of the user. The timer starts when the user clicks enter. We utilize the same algorithm as before to determine if the user is standing or sitting. We track the number of chair stands when the user state changes from standing to sitting. When the timer gets to 30 seconds, the test is over and we evaluate if the user passed the test based on the number of chair stands, age, and gender. The final test is the 4-stage balance test. The goal of this test is to assess the user's static balance. To do so, we measure the time the patient can hold for each position without moving their feet or needing support. Each stage with increasing difficulty involves the user placing or lifting their feet to specified position as shown on this illustration. If the user can hold the pose for more than 10 seconds, then they pass that stage. If the user is able to pass every stage, then they pass this test. Shown here are all 4 balance tests. Our algorithm looks at the feet to determine if the user is able to keep balance. If the user moves their feet or lost balance, then the user fails the test. For the first 3 stages, both feet are on the ground. As a result, we use the same algorithm to determine if the user moves their feet. This was a trickier challenge than anticipated because Mediapipe tries to fit a human model to the whole body. As shown in the clip, when your upper body moves, the Mediapipe body model moves your feet sometimes, even though your actual feet are stationary. In order to overcome this shortcoming, we implemented optical flow with our Mediapipe post-estimation. For the first frame, we used Mediapipe to identify the initial positions of the toe, ankle, and heel of both feet. For the following frames, we used optical flow to track the 6 feet positions. When the user feet moves beyond the threshold, then the user lost their balance. This method improved our accuracy significantly because the feet positions no longer moved when the upper body moved. However, one disadvantage is with occlusions. For example, when one foot is hidden behind the other, our algorithm doesn't recognize if hidden foot moves. However, that hidden area is quite small, and it is unlikely if someone loses their balance to stay within the hidden area. For the final stage, our algorithm needs to determine if the user is able to keep left foot off the ground. This is a tricky challenge because Mediapipe gives us no environmental information. However, Mediapipe can give us the position of the joints with respect to a coordinate system whose origin is located at the center of your hip. When both feet are on the ground, the y distance of the 2 feet from the center of the hip are approximately the same. As a result, if both ankles' y coordinates are approximately equal, then both feet are on the ground and the user fails the test.
As discussed in previous sections, Mediapipe alone was insufficient for determining certain poses. The image on the left shows the jitter in the trajectory of the right shoulder position provided by Mediapipe as compared to the true shoulder position. And as you can see in the video, both the right elbow and feet suffer from severe jitter. In order to combat this, we tried several methods to improve Mediapipe's output: Gaussian blur, optical flow, and Kalman filtering. But before moving on into detail about these methods, I think it's important to talk first about how Mediapipe actually works. Mediapipe is built on BlazePose, which is a machine learning model which was developed by Google. It works by taking the first image of a video and running it through a detection model. This model identifies the person in the frame, draws a region of interest around that person's body, and finds 33 key points. These are like joints and facial features. This step is computationally expensive though, so it's only performed on the first frame and any frame where the person moves out of the camera's view. In each subsequent frame, the image is run through a tracker model. This model compares the current pose to the next image and moves key points to new locations. Next slide. Since Mediapipe uses neural networks for its joint detection and tracking, it is susceptible to adversarial attack and contextual bias. This essentially means that the neural networks can be fooled by slight perturbations in the background of an image or slight differences in the subject being identified. This can take the form of cluttered backgrounds causing detection issues, solid colored clothing causing issues for tracking, etc. But by adding Gaussian blur, these perturbations are smooth, which makes the joints easier to find and track. While this does improve jitter slightly, the overall effect on Mediapipe's output is negligible. Optical flow, though, is a computer vision technique whereby pixels in 2 consecutive frames are compared to determine how far they moved. Knowing this, along with the time difference between the 2 frames, allows you to calculate the velocity of those pixels. Using Mediapipe to provide pixels of interest, we then use optical flow to track those pixels as they move through space. This is the method we use to determine if the person's feet move during the balance test. While useful in that case, this method does not improve the accuracy of Mediapipe's output on its own. While optical flow uses Mediapipe's output as an initial guess of the position, a Kalman filter directly uses the output to improve the accuracy of the system state estimation. A Kalman filter works by first setting an initial guess of the system state at time t-1. In our case, we use the position of the right shoulder, its velocity, and acceleration as the state variables. Then, we use the dynamics of the system to predict the location of the right shoulder at some time in the future t. Since this is a prediction using the initial guess of the state, there will be some uncertainty or noise in this predicted location. Once the system reaches time t, a measurement is taken in this, which in this case is a new position of the right shoulder. We know from previous videos that this measurement can also be pretty noisy, though the Kalman filter takes care of this uncertainty in both the dynamics and measurement by combining the results of both through some linear algebra and statistics. This produces a more accurate estimate of the position of the right shoulder than you would get using either dynamics or measurements alone. For the purposes of this project, we opted for the Unscented Kalman filter, or UKF. This is a variant of the Kalman filter, which allows for the use of nonlinear dynamics. For our system model, we chose to use a second-order kinematic model of position. While this model is linear, the use of a UKF over a regular Kalman filter does not impact the accuracy of the output, and in fact, allows us to implement more complex nonlinear dynamics in the future without the need to rework the code. Essentially, we're future-proofing. While Mediapipe provides the position of the shoulder, we need a way to get the velocity and acceleration of the shoulder as well. For this, we tried two different methods. The first involves comparing the position of the shoulder in subsequent frames to calculate both velocity and acceleration. The second method uses optical flow to calculate the velocity of pixels in a region around the joint. This velocity is then used to calculate acceleration in a similar manner to the first method. So before moving on to the results, I just want to quickly touch on how we performed our benchmarking. Since we didn't have access to a high accuracy Vicon or OptiTrack system, we instead opted for the cheap solution of placing a red sticker on the shoulder of the person being tested. By looking at the position of this sticker relative to the shoulder position, we were able to come up with a bias, which essentially moved the known sticker position up to the shoulder. During testing, we made sure to keep the arm stationary relative to the shoulder so that this benchmarking method could be used to compare the outputs of each method to a known true position of the shoulder. While we know that this method isn't 100% accurate, since both raw Mediapipe and the improvement methods will all suffer the same inaccuracy, we figured the results will still be valid. Overall, the UKF and blurring do offer an improvement over base Mediapipe output when using the frame difference method for UKF. Generally, UKF improves the accuracy of Mediapipe by roughly 2 millimeters, while blurring images improves the accuracy of Mediapipe and subsequently UKF by roughly 0.3 millimeters on average. However, when we use the optical flow method to determine the velocity for the UKF, it proved to decrease the accuracy by more than double Mediapipes. In the worst case, optical flow added an additional 80 millimeters of error. Looking further into this, you can see here in the screenshot that the UKF result lags behind the Mediapipe and true position by quite a bit. This is most likely due to inaccuracies in the optical flow velocity calculations themselves. As stated previously, optical flow compares the pixels in 2 frames to determine how far they move. This is all done via the intensity or color of those pixels. In the case of these tests, you can see that the region surrounding the shoulder is primarily one uniform color. This prevents optical flow from getting an accurate reading, as the delta between 2 neighboring pixels is very small. This makes it hard to distinguish one pixel from another and essentially tricks the algorithm into saying that these pixels don't move. This is why optical flow is better suited for tracking corners or areas where pixel intensity changes dramatically from pixel to pixel. Think like a QR code. Seeing that the UKF had a positive impact on the accuracy of Mediapipe, we sought to further improve this by adding additional sensors. In particular, we used an IMU inside of a phone. An IMU is a sensor package which consists of accelerometers, gyroscopes, and magnetometers, which measure the device's acceleration in space, its angular velocity, and its orientation. Using these, along with the initial readings of the phone's orientation in space relative to the camera, we were able to process the accelerometer data to provide the acceleration in the X and Y directions in the camera's inertial frame. Having a direct acceleration measurement reduces the noise of the system's state measurement and ended up improving the accuracy of UKF even further. The accuracy improvement of the 2 steady assessments we tested with this method saw an average improvement of about 3 millimeters, with the stand-up and walk test seeing an increase in 5 millimeters. Overall, our project was able to guide a person through the steady assessments and track them automatically using Mediapipe. We were then able to compile a report of the results and notify the user if they were at risk of falling. Through methods such as through methods such as Gaussian blur, optical flow, and unscented Kalman filtering, we were able to improve the accuracy of Mediapipe's output. Finally, by including IMU data, we were able to further improve Mediapipe's accuracy to visible levels. In the future, we would like to implement more complicated dynamics based on body kinematics. This should allow for more accurate tracking of joint positions. Additionally, we showed that the addition of a single IMU sensor improved accuracy by roughly 10%. By implementing a series of cheap IMU sensors, we could further improve Mediapipe's output for full body tracking, though the most immediate impact of these sensors would be on improving foot tracking. Using these IMUs, we could eliminate the need for optical flow workaround methods we are currently using. Any questions?
Thank you. Great job. So let's open up the floor for questions. And well, while I'll start with one, just kind of on the, I guess more on the product side. The IMU, what do you think the added costs would be if you added IMUs to the system?
Yeah, so I think like one of the challenges is like IMU sensors are relatively quite cheap. And I think that that's more of an inappropriate setting for the at-home case, because that's asking someone to buy a bunch of set of sensors, get them connected to the computer, and then running it at home. But what we envision is like you could have an at-home assessment that kind of roughly tells you if you're at risk, and then in a more of a clinical setting where we have more standardized, where they can afford to pay for a little bit higher upfront costs with IMU sensors, and someone who's trained, you can get fairly accurate pose estimations, we think, by adding these IMU sensors, which are only, you know, a couple dollars each, but really the issue is getting that wireless communication and syncing and making sure everything's calibrated. So those are the big challenges that we had to do some more complicated workarounds, but it does allow for a lot more opportunities, as Zach pointed out.
Any other questions from the audience, comments? Too bad Rujana is not here. Rujana is always famous for asking tons of questions. Let's see. So if you look back at the past work, I know there's a lot of stuff that you did in terms of figuring out the problem, looking at, you know, potential ways of addressing different things and exploring a bunch of different avenues before you came up with the one which you have. If you think about one of the ones that you didn't end up focusing on today, what do you think is the most promising near-term technology?
Yeah, that's a great question. I think one of the potential ways that could have been pivoted is trying to do gamification for physical therapy for any people. So not specifically for the elderly, but just people who have who do physical therapy and need physical therapy. Through our interviews, one of the major things through our interviews, we interviewed a physical therapist, and he said the number one way you can make sure that, you know, you see growth and you see improvement is the exercises they do at home. Like they may be at a session for like 1 hour, but then for the rest of the week, they're going to be at home doing these exercises, and having that good adherence and improving that adherence is key for seeing patient improvements and outcomes. So one of the ways we could see it potentially be another alternative avenue that we could have explored was doing physical therapy, like at home camera-based kind of technology for tracking and everything, and making it fun for physical therapy patients.
And also, so beyond elder care, also,
yeah,
just
exactly.
physical therapy.
Just like a broader set of group of people.
Wonderful. Any other comments, questions from the audience? Okay, well, let's give them a hand one more time, or virtual hand. Thanks, guys.